What I want to talk to you about today, to a large extent, is all the real things in the real world that all the analysis we've done so far doesn't quite let us deal with. Okay, because we've been taking quite a simplified look at the world in producing our models, our transfer functions, and how to deal with them. Okay, so we've not really approached some of the nastier bits of engineering. We've kept it nice and clean. So what we're going to look at today is some ways, and this is just qualitative. I'm not going to be doing any analysis today. I'm not going to be doing any sums, if you like. Just so that we understand some of the issues that you might come across in the real world to do with nonlinearity, to do with discrete time. Well, those are the two biggest issues, I guess. So real world issues are to do with the effect of sampled data, okay, and how that affects our understanding of control. Different ways of modeling systems. All we've done so far really is we've taken a transfer function, which is, to all intents and purposes, it's a high order differential equation, just rearranged a bit. And we look at some different ways of modeling systems. And on the bottom line of that, what it should say is we'd look at nonlinearities. Okay, because everything we've looked at so far, we've assumed that our systems are all linear. Every single one of those mass spring damper pictures that you've sketched or you've seen up here, we've had a very simple, for example, a simple linear spring, F equals kx. Okay, not all springs are linear. So we'll see how we can deal with that as well. Okay, so fairly lightweight kind of lecture today, really, just a bit of a discussion about issues. Okay, we've spent all of this module so far talking about transfer functions. Okay, perhaps at the beginning of the module you'd never heard of a transfer function, but you certainly understood differential equations. Yeah? So what the transfer function is, essentially, it's a higher order differential equation, maybe just a quadratic, a second order differential equation, or higher still, that relates to variables. And typically in our case, the variables that it relates are what we think of as the input quantity and what we are interested in as the output quantity. Okay? So that's all a transfer function is. It's a higher order differential equation. It is also possible to represent these systems, instead of having one high order differential equation, as having a number of first order differential equations. Okay, so, but why? Why would we bother to do that? Because if you think about it, the transfer function presentation has got some restrictions. Okay? A transfer function can only ever relate one input to one output. Okay? And quite often that's not enough. Quite often we need to have, real systems are way more complex than that. Real systems have got interaction between different inputs, different outputs. If you think of something that has got a lot of control around it, something like a gas turbine engine sitting on an aircraft wing, there are so many different variables that all interact. Simply modeling it as a transfer function is really way too restrictive, okay, because it doesn't allow us to look at the effect of multiple inputs and multiple outputs. So part of the reason that we look to this different modeling method is to give us a bit more flexibility. Okay, and what we're going to do is look at taking our differential equation, high order, sort of second order, third order transfer function system, and representing it as a bunch of first order equations in a specific matrix format. Okay, and if we do that, you'll see in just a second that we can develop a very much more flexible approach to modeling. There you go. That's the format. Okay. I hope there's some words to go with that. I'll explain it if not. So if I've got, let's say, a third order system with a third derivative term in it, I could express that as a third order transfer function. Okay, we've done plenty of that by now. We know about that sort of thing. I could alternatively express it as 3 first order differential equations. Okay. And in order to do that, we've got this particular layout that we use, and this whole technique, if you're looking up in the in the index of a control book, what we're looking at now is called state space representation. Okay, state space. And these are state equations. To make state space work, what we need to do is to choose a particular set of variables. Okay, x1, x2, x3. We choose what they are. And you can see what we've got here, if you look at the shape of this, is x1 dot, first derivative equals some coefficient times these state variables plus something times the input. Okay, u is the input quantity. x2 dot, the first differential of the second one, is equal to some coefficients in a times the state variables. And we can construct these. Very often, some of these are dead easy. Because you might find, for example, that if this is, say, a position thing, one of those state variables might simply be that if x2 says is position, is displacement, then x2 dot is simply velocity. And I might make another of my variables velocity. So some of these equations are dead easy. And so you usually get one of them with loads of coefficients and the others with 0, 0, 1 or 1, 0, 0, quite simple ones. But fundamentally, all we're doing is we're modelling our system in terms of state equations, which are first order differential equations. Okay, that is the state matrix, contains all the coefficients. That's the input matrix if there's a direct interaction with the input quantity. Okay, halfway there now. But the trouble is we haven't, that set of equations at the top doesn't take us to the output. It's just telling us about these things called state variables, which are kind of internal to the system. So we need a second set of equations to relate the state variables, the x's, to what we think is the actual output. So these are the state equations, these are the output equations. Output equals some coefficients times the state variables, plus there might be a direct link through to the input. In many cases, that D matrix is a 0, but at least the structure allows us to put it in there. Okay, and that's a state space representation. Now, we're not going to do any of these. We haven't got the time in this module, but you can see that it's a different way of representing things. The key thing now is, if you know enough about matrix algebra, we could make this input scalar u, we could turn that into a vector. Okay, so we could incorporate, by turning this thing here into a matrix, we could incorporate the effect of more than one input quantity at the same time. Similarly, if we turn this into a matrix, y1, y2, y3, we can express more than one output at the same time. Okay, so by building these first order equations and putting them into this particular form, okay, we can relate multiple inputs to multiple outputs, okay, which is something we can't do at present. Okay, what else can we do with these, I wonder? Well, we can do all sorts of things with these in terms of control techniques. We can build complete controller systems based around the state variables. Now, the state variables are sometimes internal. They're things that don't really exist in a physical sense. But we can still have got some very, very powerful control tools that we can do based around these state variables. It's done that. That representation is known as state space, and the equations represented are the state equations. That's the top line. Okay. I've just said all this, really, can't I? We can extend these quite simply to deal with multiple inputs and multiple outputs. Right, let's not go to time just yet. So that's one concept I want you to get hold of. The stuff that we've done is really quite limited. Transfer functions relate one input to one output. And that's all you've got. When we move to state space representation like this, we can relate multiple inputs to multiple outputs. We've got the maths allows us to do that because we've moved into kind of a matrix modeling structure. Okay. The other thing it allows us to do is some interesting control techniques where we can work with controllers that use these state variables, even though they might not be something you can physically measure. Okay, so we can introduce some really quite interesting modeling techniques based on that. Again, we haven't got time to do that. This is just to give you some idea of where this might go. Right, the other thing that I need to talk to you about, again, a bit qualitatively, is time. Okay, and this is all to do with the restrictions of what we've looked at so far. We've described all the systems we've looked at, okay, with a differential equation. And a differential equation, by its very nature, exists in what I would call continuous time. Okay. Let's see if I can persuade you that they're no good. Go away. Okay, that's a typical signal against time. If you cast your minds back to when you were very, very first introduced to differential mathematics, okay, way back probably in school, when you were first introduced to differentiation, how did the maths teachers introduce you to what a differential is? The area would be the integral. That's how they introduce you to integral, which is just as good in terms of explaining this. But how did they describe a differential? The gradient. Okay, so we start off with a little graph like this. And if we're introducing the concept of in this case, dy by dt to somebody who's not met it before in maths, what you'd probably be introduced to is, well, if you look at time 1, time 2, y1, y2, okay, and you work out the gradient between them. And that generally is how we're introduced to the concept of the differential, isn't it? And you might say that the gradient is equal to the change in y over the change in time. Yeah, ring any bells? Probably a few years ago now when you first introduced to that, but typically that's how it does it. What turns that from being delta y by delta t, or if you prefer, delta y by delta t, how does that become a differential? dy by dt. What makes it become a differential rather than that delta y over delta t up there? Yeah, it's the delta y is y2 minus y1, and delta t is t2 minus t1, and that's how you would. But that I think you'll agree is the average gradient between those 2 points, isn't it? The differential is the gradient at a point. Okay. So what do you have to do to these numbers to turn it from being that delta y by delta t into a true differential? What's the nature of delta t? What's the nature of dt? It's a real memory test, this one, isn't it? If this is going to turn into a differential, what has to happen to delta t? It's got to come together such that delta t becomes how big? Yeah. It tends towards 0. So what turns this from being an average gradient kind of calculation to being an actual differential is that delta t, or delta t up here, or that delta t, has to trend towards 0. Yeah? Does that make sense? Okay. So T2 and T1 come together to be effectively the same place, and that's what makes it a true differential. Right, let's ask you a question about computers then. Let's get rid of all this. Quite a lot of you, you've been doing quite a lot of experimental work, maybe to do with some of you with your final year projects and things. If you're measuring a variable like this with a digital computer, okay, so you're connecting up some kind of interface card to the real world with your PC, how close together can you get T1 and T2? Depends how much money you've got, basically. It depends on the speed of the I/O card, it depends on the speed of the computer, all those questions. And a lot of that is down to how much money you pay. What I'd like to suggest to you as the principle is that there is a finite limit to this. Okay? If you go and buy an analog to digital input card for your PC, it takes a finite time to measure that data, convert it into the right format, shove it into the PC, do whatever the computer needs to do at whatever speed it can do it before it can look again. Okay? So there is a limit to what you can do with delta t in any kind of digital system. Okay, so that quantity in there is restricted by the hardware. So in fact, if you were to sample that, and then have a look at the information that you've got in the memory of your digital system, what you've actually got isn't a continuous curve at all. Okay, it's a number of discrete points. And I'm going to label that slightly differently. Okay, because there's a finite time in between each sample, then the information available inside your digital system actually only exists at discrete points in time. Okay? It's what we'd call sampled data, and we can sample it once per so many milliseconds or microseconds or whatever it is. Okay, so that's the first sample, that's the second, that's the third, and so on. So we get discrete numbers at discrete times. Okay, so the question now is, if I've got this sort of data, can I actually get a true differential? No. Why not? Yeah, I cannot make delta time approach 0 because it's restricted by the fact I'm now operating in a sampled data sort of environment rather than what you and I live in, which is a continuous time environment. Okay, so strictly speaking, we can't do differentiation on that system. Okay, which then says, well, all the theory that I've done so far has been about differential equations and their behavior, and if I'm looking to implement any of this stuff on a digital machine, then differential equations stop making sense to some extent, okay, because I've got sampled data. So if I wanted to know the gradient at, let's say, this point, I can't do it by differentiation. Okay. So this is one of the problems we've got with sampled data systems. Now, the smaller you make this gap, the better life gets, and that involves throwing money at your PC. Get a faster one, get a bigger one. But realistically, we cannot get past the delta x or the delta y by delta t sort of stage. So again, back to kind of school calculus. If you're trying to work out the gradient in here, we can't do it by a differential equation. We can't do a d by dt process, but what we can do is we can approximate it. So we can take the difference between the two y values, that's yn, that's yn plus 1, and divide by my sampling period, which is delta t, or big T in this case. Okay? And that is an approximation to differentiation. Okay? We can also approximate an integral. Go back to school when you were first taught about these things. How would you approximate an integral from that? Somebody said it earlier on. You work out the area underneath. Okay? And if you're working out the area underneath, what you would do, presumably, is you would come up with some approximation, let's say the trapezoid rule, and you say, well, yn plus 1 plus yn, divide by 2, and times the time. And that would give you the area beneath. Okay? So again, we can approximate differentiation and we can approximate integration. And if nt, and if t, the sample period, is short enough, then it's not really a huge problem. We can get quite accurate results. If t is too big, we lose the accuracy. Now, the effect of all this is that instead of developing differential equations, what we've got is we've got equations that look a bit more like this, okay, with kind of indexed things. Yn plus 1 minus yn, where n represents the number of the sample. So what we need to do is all the stuff we've done so far on differential equations, okay, and we pick it all up and we put it firmly in the bin. Okay, because it's not appropriate. What we do instead is we introduce the idea of difference equations. Okay, and this is a simple difference equation, because what these difference equations involve is, instead of d by dt's, it involves the difference between two discrete numbers. Yeah? You get the idea. So we introduce a whole bunch of new maths. And because we've taken all our differential equations and put them in the bin, what's gone along with them is the usefulness of the Laplace transform. So the S operator has also disappeared off into the bin along with all these differential equations. So what we need instead is a similar mathematic tool to make sense out of these things. And what we introduce is called the Z operator. I've probably got this on the slide, I'll rattle through them in a second. Where the Z operator represents a delay of one sample period. Okay, so we can build up difference equations, and instead of having a notation n plus 1n, all this kind of stuff, we could use an operator Z that represents a difference of one sample period. Okay. So there's a whole other bunch of mathematics. The nice thing, if you do move on to look at more advanced control techniques, is that once you get into this stuff, it's actually very, very simple. Because it's just subtractions and additions, really. It's very simple to deal with. But it's not in our syllabus, so I'm just telling you about it. Let me just erase some of this stuff I've got on here. If I can. Close enough. So, what we've done, the study that we've done, the analytical tools that we've produced, they're all based around continuous time, the sort of thing that you and I live in. Okay? Digital systems, and let's face it, many things these days are controlled digitally. One of the drawbacks of the digital system is that as well as being discrete in an amplitude sense, you know, you can only go in steps in a digital representation, we've also got a discrete time. We've got sampled data. So we get, instead of having nice smooth curves on our data graphs, we get like this collection of lollipop sticks. There's spots every so many, well, it depends how often you're sampling really. Here's the traditional approach of differential equations. Doesn't work anymore. It's no longer appropriate. I just said that. So we introduced this concept. Instead of the differential equation, we've got a difference equation. And because we can't really use the Laplace operator, because this is all to do with the differential approach to things, we introduce a Z operator. So when you look at these digital kind of models, and you can represent things using difference equations in state space that I just talked about before, just as easily as you can differential. Okay. Hastily prepared slide. You can tell I can't spell linearity properly, so sorry about that. Just spotted it. So I'll pause. So that's two things then that we can't do yet. Okay. We've got sampled data systems, and we've got multiple input, multiple output modeling techniques. The other thing that we can't do is non-linearities. Okay. Have you all now done the Simulink tutorial where you did the cruise control, the vehicle acceleration speed control? Did that go okay? No? Not good? Okay, well, it's worth practicing. Persevere with a Simulink because you're going to need it for what I'm going to talk about next, which is your assignment. Okay, so you will notice in that model on that exercise, okay, if you recall, whoops, go away. If you recall the model for that Simulink exercise, okay, on the one side you had a throttle pedal, it's meant to represent a throttle pedal as the input quantity, okay? But in order for that to be sensible, as part of my block diagram, I had a limiter. Okay, the first thing you met in that model, starting from the left-hand side, the first thing you met was actually a non-linear element. Because in the real world, if you imagine this is actually your throttle pedal in the car, it can only take so many different positions. Okay? If you press it down too far, the floor gets in the way, so it stops it. And if you release the pedal completely, there's some kind of stop that stops it from going up and hitting underneath the speedo. So there's physically only a limited number of positions that can take. In order to represent that in the model, I had to introduce this block which limited the motion of the pedal between 0 and 100%. I think we gave a number of something like, I don't know, 60 millimeters, whatever it was, 100 mil. Okay? But in between those two places, its behavior was linear. Okay? So even the simplest kind of system, like this cruise control, the throttle pedal, to model it properly, we can see that it is non-linear. I won't start talking about the engine, which is also not linear, but we'll just forget that one for now. So we need to come up with some way of dealing with non-linearities. Okay, so another problem with the real world is that a lot of it is non-linear. Whereas everything we've learned so far is based around linear systems. So we've got lots of new techniques to deal with the non-linearities that we find in the real world. Okay, so we can make linear design theories work. Now the trick is with this is actually quite good, because many of the theories that we apply to non-linear systems are actually fairly unsophisticated ways that lets us pretend that they're linear. Okay, because we understand linear things, because hopefully by now you've got some understanding of how we control linear systems. So if we can find some fudge factor, some fiddles, to make these non-linear things appear linear, then we can just keep using the linear theories. Okay, I'm not going to go into these particularly, but just some words to give you some idea of how we do that. There's this concept of piecewise linearization. Let's say I've got a transducer. As part of my control system, I've got a measuring device, a transducer, but that transducer isn't actually very linear. It's got some kind of non-linear behavior. Okay. What we do with piecewise linearization is we say, okay, let's accept that this is non-linear, but just say, if I'm operating on x values between there and there, it's linear, and it's that blue line. If I'm operating on x values up here, it's linear again, and it's that red line. And then if I'm operating up here, it's linear with a different gradient. So what I'm doing is I'm chopping the non-linear curved sort of response up into lots of little pieces and pretending that they're linear. So the coefficients, if you like, of this device vary depending on what value x is. So we get piecewise linearization. You can see where the name comes from. Okay, so you get, in this case, 3 different equations describing that thing, and which one you use depends on the value of x. That's actually not as bad as it seems, because a lot of control systems are designed to keep the system in a fixed place. If you think of things like process technologies in pharmaceutical industry, food industry, you're trying to control temperatures in many cases to a fixed point. So really, in lots of cases, although the systems might be non-linear, your controller's trying to keep them around a fixed point so you can pretend it's linear just either side of that point. And it's not just the food industry. Certainly, I know of some generations of aircraft engines that this is exactly how they model gas turbines. You just split it up into straight lines. Okay, and that's really quite a sophisticated piece of equipment. So that's piecewise linearization. As I said, these were very hastily prepared. You'll notice these are different to the ones I put on Blackboard earlier in the week because I realized half the slides were missing. So I've updated it. I'll change them over later today. Describing functions, well, let's think of a different sort of nonlinearity. And here's a different sort of nonlinearity. Okay, that's what I would call a discontinuous nonlinearity. The one I just drew then was a continuous nonlinearity. It was curved. This one I would call discontinuous because it's basically got step changes in it. It's got corners in it. So what you've got here is a situation where in x values up to there, it behaves in a particular linear sort of way. And in x values up there, it behaves in a different linear sort of way. Okay, so this is a technique called describing functions, or functions. where we model the two different types of response separately, and this is a graphical technique. Okay, so you'd actually produce pictures. You'd produce kind of vector diagrams of what the system's doing, and depending on how you arrange your controller, well, putting it crudely, you take the two different pictures and you cut them up the middle, and that middle represents the switching point, and you join them together, and you can then produce a describing function which shows you the behavior of both halves of that system joined together with this switching device in the middle. Okay, that one's quite good fun because you can physically do it with a pair of scissors and sellotape, so it's quite visually easy to see what's going on. The other one is phase plane. I've got that wrong. Phase plane is the pictorial one, beg your pardon. Phase plane is to do with looking at what happens to the state variables as things change around, and that's the one where you glue the two pictures together. Sorry about that. Okay, describing functions is a mathematical technique. Again, this is stuff we don't have time to talk about. If you go back in time long enough, because about 50% of you guys are mech eng, I think, aren't you? If you go back far enough in time, you guys used to do control the same way the errors are in year 2, and there was a final year option where we could do all this fun stuff with nonlinearities in discrete time. Regrettably, that's not available anymore. You might not think that, but I do. Okay, so those are some nonlinearities. Right. That's all I really want to tell you about state space, discrete time, and nonlinearities. Okay? They're all improvements on the straightforward transfer function approach that we've taken. Having said that, the transfer function approach and the stuff that you've learned to date is extremely powerful, and in many cases you don't need to know about this unless you move into more sophisticated control territory. Okay? You can do a huge amount using the traditional techniques that we've considered. Is that okay? Purely qualitative stuff, no calculations involved, but just so that you know that there's more to this.